Welcome, intrepid viewers, to Skills for AP Science. This is podcast number 1. We are going to be covering significant figures today. Significant figures really come in their own when we start talking about mathematical problems and how many numbers to report at the end of it. But in reality, significant figures, at least in science, comes from this idea of measurements. Any measurement that is taken in science, which is the main source of all the data in science, will have a specific level of certainty and uncertainty. So significant figures, often seen in textbooks as sig figs, and I will use these terms interchangeably, and occasionally even seen as significant digits, although I tend not to use this term. Since significant figures are just this concept that value of any measured or calculated quantity will have a level of certainty. And the significant figures are what numbers or what actual digits are certain within that value. So if we look over here at my eggs, and let me get my pen here, this is a counted quantity. Significant figures do not actually apply to counted quantities. I count each one of my eggs and I come up with 12. I have exactly 12 eggs. I don't have 12.1 eggs. I don't have 11.999 eggs. I either have that 12th egg or I don't. So that last number isn't a measured number, but actually a counted number. This is a concept that is often overlooked, especially by many of my chemistry students. Significant figures also do not apply to common conversion factors. These are accepted conversion factors, not ones that you have calculated or come up with in the course of a lab. This is things like 12 inches to 1 foot. Every time I have 1 foot, I have exactly 12 inches. Now, significant figures do play a role in any measured or calculated value. Any measured value is technically an approximation. There is a certain level or specific level of certainty and uncertainty. Even if I really zoomed in and took a very close look, if I measured something to this point right here on this line, I would have to make a determination of, is it going to be closer to this line, closer to this line. Even if it's exactly on that line, you notice there's a certain width to this line. And this line is an approximation. It can be a very accurate approximation, but is not specifically exact. So if I take a mass of an object, let's say this weight down here, and I mass it or put it on a scale and find its mass to be 65.8 grams. What I am actually saying when I record this digit is that this 8 is going to be my level of certainty. I have an uncertainty of plus or minus 0.1 grams. This could really be 65.9 at its most extreme or 65.7 at its least extreme, but most likely it's 65.800 something. Using significant figures keeps us from appearing to be more accurate than the equipment we use really allows us to be. And this again is important in being honest with the numbers that we record. So let's start figuring out how many significant figures a number has. Anytime you see the number 1 through 9, any non-zero integer is considered significant. So if I have 258 written out, both the 2, the 5, and the 8, each one of those are going to be significant. I would have 3 significant figures. Likewise, 12.25, each one of those are non-zeros. I would have 4 significant figures. Leading zeros are not significant. They are placeholders. So here I would have 0.00000511. All those zeros I said is just telling us how small this 511 is. So none of those are going to be significant. If I take each one of those out, I am left with 3 figures that are actual measurements. Likewise, in my number 0.05114, I would have 4 significant figures. So if I take a look at this number, 0.0052529, how many significant figures would I have? Most of you, it's probably quicker to count the significant figures than it is to actually say a number like that, but I would have 5 significant figures. These zeros here are not significant. The rest of these digits are. Rule number 3 when looking at significant digits. Zeros between non-zero integers, otherwise known as captive zeros, are significant. Here I have 205. Now if I only looked at rule 1 and 2, the 2 and the 5 we know are significant. But here this 0 is captive. It's in between the 2 and the 5. Okay, like it's captured or between those brackets. Therefore it is significant as well. So I have 3 significant figures. Here with 0.05008, and yes, I said an extra 0 after the decimal place, I apologize. These first 2 zeros are not significant. They're just placeholders. The 5 and the 8 are significant, and so are these 2 zeros because they are captive. Now, trailing zeros can either be significant or not significant depending on a couple rules or instances. The specific rule is if there is a decimal place, then trailing zeros are significant. Here I have 1000.00. Because of that decimal place is telling me that all of these zeros are significant. I wouldn't have written these 2 zeros down here unless I actually measured it to that level. Here I have the quantity 100. Now this only has 1 significant figure. That 1 is not a 0, therefore it's significant. These 2 zeros will not be significant because there's no decimal place. These are just placeholders, much like the placeholders we saw in rule number 2. Now I have the same quantity, 100, but I have a decimal place. And you'll see these a lot in science questions. This is indicating that it has been measured all the way to that ones place. So I would have 3 significant figures. So take a moment, pause the video, and determine how many significant figures each one of these has. Hopefully you've worked that out. If not, go back and pause. I'll go ahead and start going through these. First one's pretty easy. We will have 2 significant figures. For the second one, we will have 3 significant figures because we have that captive 0. That one counts. For the third one, we only have 2 significant figures. This is because the 3 after the comma are just placeholders. In my next one, I will have 2 significant figures, both the 5 and the 8. In example number 5 here, 72,001, I have captive zeros, therefore I have 5 significant figures. I will also have captive zeros in the next one, which will give me again 5 significant figures. Now getting a little bit tricky on the last 2. So here on number 7, we know the 5 and the 2 are significant. We have captive zeros which are significant. We also have trailing zeros. Now these trailing zeros are in a number with a decimal place, so they also count. I will have 6 significant figures. And the last one, I will actually have 4 significant figures. The 6 and the 7 count. My trailing 0 count because they're after the decimal place, but all my leading zeros do not. So now we know how to determine how many significant figures there are in a number. How do we use that in math problems? Well, there's 2 flavors or 2 rules when it comes to using significant figures. The first flavor is the multiplication and division flavor. Sounds really tasty. Ask for it next time you get ice cream. In multiplication and division, the results should be rounded off so they have the same number of significant figures as the components with the least number of significant figures. So here I have 2 numbers multiplied together. I plug those into my calculator. I will get this number, 3,136.764. Now this is far more accurate than my two numbers to begin with. My first number has 3 significant figures. My second number actually has 5 significant figures. If I look at this number, I would have 1, 2, 3, 4, 5, 6, 7 significant figures, more than I need. So I'm going to need to round it down. I'm going to round it down to 3 significant figures. So that would be my first 3 numbers. I need to go to this place here where the second 3 is. Look at the one below it. It's a 6. That means it rounds up. I get 3,140. And with all good math problems, as you start writing all these out, go ahead and put a box around your answer, and that will really help those that are grading your papers, and even yourself when you look back at it, know what your final answer is. With addition and subtraction, we have a slightly different rule. This is the number of decimal places in the result is the same to the least number of decimal places used in the calculation. We're not talking about specifically the number of significant figures, but the least number of decimal places, where that last significant figure was. So I have two numbers. I have 321 grams minus 80.018 grams. Put that in my calculator. I get 240.982 grams. Now my first number here, my least accurate is going to be to the ones place. In my second number, I'm actually all the way out into my thousandths place. I use the least accurate one, that is going to be my ones place. That's what I'm going to round to in my answer. So my answer actually comes out to 241 grams. As always, put a box around your answer. So here I have a question. Go ahead and pause the video and work it out, and then come back and we'll go through it together. Hopefully you've done that, so let's work through it together. I plug all of these in and I get 296.05. Now this is an addition problem, so I'm using the second rule for addition and subtraction. Here I go to the hundredths place in the first number, the ones place in the second number, and the tenths place in the third number. I use the least accurate one, which is going to be the ones place, which means that my number is going to be rounded off to the ones. That will give me 296. And as always, put a box around the correct answer. We have a division problem here. Go ahead, pause the video and work it out. Now as we plug this into our calculators, hopefully, or if you're doing this by hand, you'll get this nice long number. You get 77.90909090, so on and so forth. This will actually round to 78. I have two significant figures in my second number, 3 in my first. I use the lowest one, which is the 2. I need 2 significant figures in the end. As always, box your answers. In a lot of these, I'm noticing I've rounded to the ones place. This is just coincidental by the numbers I happen to randomly choose. Quick review. All measurements are approximations. This is why we use significant figures. We use significant figures with anything that is measured and anything that's calculated. When counting significant figures, 1 through 9 are significant, all non-zero integers. Leading zeros are not significant. These are just your placeholders. Captive zeros are significant. Anything between two non-zero numbers are considered significant. Trailing zeros are only significant in ones that have a decimal place. If your number does not contain a decimal place, trailing zeros are just placeholders. Multiplication and division. My answer needs to be rounded to the number of significant figures in my least accurate component. In addition and subtraction, my answer needs to be rounded to the whatever component had the least number of decimal places. I hope this quick primer in significant figures was helpful, and I'll see you back here soon.